This video is a derivation of an equation giving length contraction during a process of acceleration. Please see the video Length Contraction Paradox before watching this video. The video Length Contraction Paradox shows that length contraction is not just a geometry exercise. Length contraction is linked to the law of conservation of energy as acceleration occurs. This connection to energy during acceleration will ultimately lead to the concepts of force being incorporated into relativity theory. To see the mathematics of length contraction during acceleration, we will first need to make a model of an object with length. For example, a rod of length L. This rod will be modeled as two point mass objects located a distance L apart at the endpoints of the rod. Each point mass has 1/2 of the mass of the rod. These 2 point masses are indicated by the circles in the figure. We will call them Object A and Object B. We will also need to connect these 2 point masses together, and we will do this with a spring. The spring is undeflected when the two objects are a distance L apart. Since our object with length is now described by 2 single points, we can use existing relativity theory single point acceleration equations to describe the motion of these objects. Alpha will be object acceleration divided by c, the speed of light. Beta will be object velocity divided by c, the speed of light. An object which is feeling a constant acceleration will be experiencing acceleration alpha sub 0. This is the proper acceleration of that object. An object undergoing constant proper acceleration alpha 0 will be observed to have acceleration alpha as seen by a stationary observer watching the acceleration. Alpha is the derivative of velocity with respect to time. It's also equal to alpha 0, the quantity 1 minus beta squared to the 3/2 power. The time it takes to accelerate to velocity beta is shown by the third equation at the bottom of the illustration, and the distance it takes for the object to achieve speed beta is shown by the last equation there, distance x, in the illustration. These equations for single-point acceleration within relativity theory have been around for many decades, although most modern textbooks do not show them. They are, however, simple calculus and can be derived easily from the usual special relativity principles, length contraction, time dilation, and failure of simultaneity at a distance. In order to model acceleration length contraction, we will first need to guess how this length contraction occurs. The first guess will be the most obvious, where object A and object B both accelerate with constant acceleration alpha 0 simultaneously. So a stationary observer watching this acceleration would see what the illustration shows. The objects start out a distance L apart when they are stationary, and they simultaneously accelerate to velocity beta. The distance that it takes for each of these objects to reach velocity beta is distance x, as given by the previous equations. So the stationary observer sees the objects a distance L apart when they are stationary, and they stay L apart all through the acceleration process. They simultaneously reach velocity beta and are still a distance L apart as seen by the stationary observer. When both objects have reached velocity beta, the original stationary observer sees them still a distance L apart even though they are moving. But an observer on an inertial frame moving with velocity beta now sees them a distance L divided by 1 minus beta squared, the square root, apart. In other words, when the objects are stationary in the velocity beta reference frame, they are further apart than they were in the original stationary reference frame. This has nothing to do with acceleration. This is a simple inertial problem showing distance L as seen by two different reference frames. This is just straight inertial relativity theory. But we see that the objects now stationary in the velocity beta reference frame have stretched the spring which connects them when the spring was not stretched before the acceleration started. So we now see a very important problem with our first guess for the acceleration length contraction law. Acceleration is not just a geometric process. Somehow, energy has crept into the model and must be accounted for. This energy needed to accelerate an object apparently includes not only the energy to accelerate the mass of the object, but the energy necessary to stretch the object as shown previously. This first guess for acceleration length contraction gives us a mathematical model of the universe which has complex energy processes included in every acceleration event, even the simplest ones. So we're going to conclude from this that the first guess is not correct. We're going to form a hypothesis. The real universe does not have these complex energy requirements. The real universe only requires the acceleration of the mass of the object, and no energy is required to stretch the object during acceleration. From this hypothesis, we will come up with the second guess for acceleration length contraction, and that is that we must not have identical accelerations for object A and object B. There's only one choice here. Object A and object B must have different accelerations, even though they are the endpoints of the same object. This sounds a little crazy at first, but if we think back to the inertial case and remember that while a rod is traveling at velocity beta, the clock readings on the front of the rod and the back of the rod are different. So time is varying down the length of the rod as it is traveling with constant speed beta. So it's not really all that strange to assume that maybe other things are varying down the length of the rod as it is accelerating and traveling at speed beta. So here is the mathematical model for our second guess for acceleration length contraction. Object B has constant acceleration alpha B. Object A has constant acceleration alpha A. The two objects start off stationary, a distance L apart. Object B requires distance xb to accelerate to velocity beta. Object A requires distance xa to accelerate to velocity beta. And when they get to velocity beta, they are observed by the stationary observer to be a distance d apart. Now, not only do the objects need a different distance to accelerate over to reach velocity beta, but the time required for each object to accelerate to velocity beta will also be different. We're going to just state here that alpha sub b is greater than alpha sub a. Object B accelerates harder than object A. That means the time necessary for object A to reach velocity beta, t sub a, is greater than the time needed for object B to get to velocity beta, t sub b. So the time it takes for the rod of length L to accelerate to velocity beta is t sub a, the longer of the two times. So what happens is object B reaches speed beta, but object A hasn't gotten there yet. So during this time interval, t sub A minus t sub B, object B is just traveling at a constant velocity, beta. And you can see in the drawing there that x sub A is relatively straightforward, but x sub B, the distance needed to accelerate object B to speed beta, that occurs early, and then you have an additional distance tacked onto that, which is object B traveling at a constant velocity beta while it waits for object A to catch up. So, at the instant the rod reaches velocity beta, which is the instant that object A reaches velocity beta, we can write down two equations from the previous figure, and these two equations are given here. These equations contain expressions for alpha sub b and alpha sub a within them, so they can be solved for a relationship between alpha sub b and alpha sub a. And here is the result. This is the relativity acceleration law for objects with length. If we go back to the view of the acceleration experiment, where the two observers are watching the objects as they have just achieved velocity beta, what we see is that the observer traveling with velocity beta sees object A and object B appear stationary in his reference frame simultaneously and a distance L apart. The original stationary observer will see the distance between the two objects being the usual length contraction formula, L, the square root of 1 minus beta squared, but this will not happen simultaneously. He'll have to wait for object A to reach velocity beta before this equation becomes true. The spring is not stretched. The mathematics showing how this acceleration law gives those results is shown in great detail in the article The Acceleration Law on the website www.newrelativity.net, along with other interesting supporting information.